Good morning, everyone. Welcome to the latest Lighting Design Lab webinar. This morning's commercial heat pump water heaters, hospitals and commercial settings. We are going to pause for about 3 minutes to allow everyone to settle in with the webinar format, and we will be back with you shortly. All right, good morning, everyone. Thank you for joining us. My name is Sean Dara, and I will be hosting this morning's Lighting Design Lab webinar, Commercial Heat Pump Water Heaters, Hospitals and Commercial Settings. We'll do a few housekeeping announcements as people continue to settle in, and let's go ahead with that. So during the class, everyone is going to be muted. Apologies for that. We would love to be able to have more of a back and forth, but as we all know at this point, given the webinar format, it's really not easy to be able to have that kind of back and forth, but there will be interactive opportunities throughout the presentation. Evan will be doing Slidos, and you'll have some opportunities at the end to run through some review. For questions, please go ahead and use not the chat feature. It says chat feature here. I need to correct that. You'll notice in your GoToWebinar interface, the little interface button, you'll notice a tab that says questions. Please go ahead and use the questions tab to ask any questions throughout the presentation. Type them in as they come in. Evan will either respond to them sort of in real time, or more likely pause and stop and answer them accordingly. It depends on what the question is. So please go ahead and do that. Please participate in the online polls. Those will be through Slido. Evan and Christy will go ahead and walk you through how all of that stuff goes. After the class, there will be a brief survey that as you're leaving, you'll notice that GoToWebinar will give you a link. Please go ahead and fill that out. That's extremely useful for us, both to understand how we've done, but also it gives you an opportunity to tell us what additional educational opportunities would be useful for us, for you, and that's extremely helpful for us. The slide deck and the recording for this class will be available on the Lighting Design Lab webpage. It usually takes 3 or 4 days, but go there, lightingdesignlab.com, go to the Education tab, and you'll find basically all of our recorded webinars. Also, if you have questions, you can either email me, Sean Dara at seattle.gov, or lightingdesignlab@seattle.gov. And of course, this is presented by Lighting Design Lab. We are a branch of Seattle City Light, your favorite electric utility and mine. We work with a whole variety of folks, including end-use customers, trade allies, design allies, basically anybody in the building, design, construction, implementation, sales. We're here to help everyone wherever we can. We've traditionally had 4 key areas of service, right? Education and training, just like this one, developing tools and resources that you'll find on our webpage, aggregating information from a variety of different sources that we find, including attendance from a variety of different conferences that we go to, and we spend some time evaluating technology. Now, with that, I am going to take just a moment and turn things over to Evan Green from Ecotope, who will be presenting today, and Christy Bedelnick, I hope I'm pronouncing that correctly, will be moderating for Evan. I will be in the background taking care of any technical stuff that I can take care of. So with that, I'm going to say, Evan, you have control now as presenter, so please go ahead and take it away. Have a good
Great, thanks, Sean. Yeah, I will work on getting my screen shared. While I'm doing that, I'll let Christy introduce herself.
It was perfect. I was just going to pop in and say, wow, that was my plan from the beginning. So Sean, thanks for the introduction and the handoff. My name is Christy Bedelnick. I'm the Instructional Design Manager for DNR Learn, which is the educational arm of DNR International. And I'm moderating today for Evan Green, who's really like star of the show, here to talk about commercial heat pump water heaters in hospital and clinical settings. You're going to hear my voice pop in occasionally when there are questions or when there's things that need to get posted in the chat or in the Q&A. I'm also in the background as support for Evan. We're here together today for about 2 hours, and we do have plans to take a break around the middle mark, a 5-minute break. So throughout the webinar, if you feel like there are questions that you have that need to be attended to, just like Sean said, please throw them into the Q&A. We'll keep an eye on them. We'll try to tackle them right then and there. If not, there's lots of opportunities to pause and ask questions as well. And then the last thing I want to mention is that Evan is going to be using an interactive polling software called Slido. We love it because it's one of those tools you can use to engage with each other through a screen, and we find that it's really, really valuable for helping Evan address your needs, meet you where you're at, and also it just makes things a little bit more interesting. Like, it's a nice change of pace every once in a while. So the caveat here, it's not even a caveat, but I want to throw out it, say that Slido is a totally anonymous software. You don't need to sign up for anything. We're going to have some login information to this specific poll in a couple of slides, but if you could use your smart device or your tablet or even the web browser you have open right now to engage, we'd really, really appreciate that. And we use any feedback you provide. We take it very seriously to make sure that as we develop more webinars, we're meeting your needs. So thank you so much for showing up. Thank you for participating in advance. And Evan, super excited to hear about commercial heat pump water heating systems. So the floor is all yours.
Great, thanks, Christy. I want to start off asking, can you see the presentation now? Can you see my screen?
Yep, it is up. We can totally see it.
Great, thanks. So yeah, I'll start by introducing myself and why I'm here today. So I am a research engineer at Ecotope, and Ecotope is a design and engineering firm, or a research and design engineering firm based out of Seattle. And our main goal as a company is to design all electric, energy efficient buildings so we can both decarbonize the grid as well as minimize the amount of energy we're adding to the grid with these new designs. So naturally, we work a lot with heat pump water heaters because they're so efficient, and they just work really well in these commercial designs as well as residential applications. But today we're going to talk about their application in hospitals and clinical settings. So I'll put a disclaimer out there up front that I know a lot more about heat pump water heating design than I do about hospital design. So a lot of what I'm talking about today will be focused on heat pump water heaters themselves and my best understanding of how they will best fit into hospitals and really the context I have around this. And when I've worked in the hospital context was at my last position as an applications engineer at Colmac Water Heat. So they're a heat pump water heater manufacturer. You'll see their name throughout this presentation a little bit, but at Ecotope here, we're very manufacturer agnostic. We want to make sure we get the best heat pump in for each application, and there's a lot of different manufacturers that can provide that. But at Colmac Water Heat, I worked with a lot of design engineers that worked on various applications. Multifamily, of course, was a big one, but then there was also designers working on hospitals and offices. And in hospitals, they did have a lot of unique requirements that we had to satisfy with heat pump water heaters, and we did find solutions for that. So it's really encouraging that this is a good technology for this application as well as many others. And I will also let you know that I'm working out of my under construction office right now in northeastern Washington State. So that's what my great wood background is right now. So setting up an office here, I'm really excited about it and just enjoying the springtime. So today we're going to start off by talking about why we would implement a commercial heat pump water heating system. And then we're going to talk about the different types of products on the market and where they might be applied. And part of that is talking about the difference between commercial and residential systems, both size and application. And then we'll dive a little deeper into the different types of components that are encompassed in a commercial heat pump water heating system. Because we all think about the heat pump water heater itself, but really to make it work well, you have to think about it as the whole system that's delivering hot water. That's the heat pumps, the storage tanks, the temperature maintenance system, as well as the controls. And then at the end, we're going to review everything we talked about today, and then have some closing remarks as how heat pumps apply to hospitals. So Christy had a really great intro on how Slido works and why we're using it. So at this point, we can test it out, and we can go to slido.com either on your desktop, or you can go through, of course, you can go online on your phone at slido.com, or you can just go ahead and take your camera and you can scan this QR code on the left side of the screen, and then it will take you straight to the event, the Slido event that we'll use today to get your feedback. And once you're on, if you're on slido.com, you can enter this event code, HACS, hospitals and clinical settings, and that will get you to the specific questions that we'll be asking today when we bring up the Slido slides. So we'll start out with an introduction survey so I can learn a little bit more about who I'm talking to, and maybe it will help me cater a little more on the details that I'm bringing forward today. So the first question I'm going to ask is, what is your profession? So here as presenters today, as I said, I'm a research engineer at Ecotope, and I do a lot of really satisfying things. I work with manufacturers of heat pump water heaters, or air to water heat pumps in general, for domestic and hydronic heating, as well as work with the designers on our team to make sure that they actually work in the buildings that we're designing them around. So as an engineer, I get to apply my knowledge of heat pump water heaters in a lot of different ways, which is really great for me. Utility staff, so that's really great. There's a lot of advantages for the utilities for these heat pump water heaters, so it's good that we have utility staff listening in. and energy engineer. Of course, that's also a great person to learn about heat pump water heaters. And yeah, we're going to talk about a lot of ways to implement these through proper design. So there's going to be a lot of engineering related topics here. And yeah, utility efficiency program implementation. I'm really glad that these types of folks are listening into this, because it's really important that we can implement this in a really practical way, and then maybe get some incentive dollars out there to get the market going on these in different applications. So in terms of experience, where does your experience lie with commercial heat pump water heating systems? It looks like we have some intermediate experience in the audience today, which I think is going to be really good. What I'm talking about today will apply to, hopefully it'll apply both to beginners and all the way through the experience level of expert as I dive into different ways to configure these systems. So yeah, hopefully we'll get some good information out to you no matter what experience level you have. And some questions you brought with you regarding commercial heat pump water heaters. And the first question is, what are the possibilities today? And we will definitely, I'll read out these questions first, but we're definitely going to talk about what the possibilities for heat pump water heaters are today. And let's see, large demand and colder temps. Any amazing way to avoid the huge electrical demand of backup resistance heating? Yeah, we'll talk about that as well, with different refrigerant types that can operate down to lower temperatures. And then what are some of the benefits of using a heat pump for water heating? We'll definitely talk about that as well, and that's actually one of the first things we'll talk about today. So I think we're all in a good headspace, and we're definitely asking the right questions today that hopefully I'll be able to answer for you. And feel free to ask any additional questions throughout. Christy's really good about bringing those questions in when it makes a lot of sense for our conversation. And I love answering questions outside of the normal prompt about what I'm talking about. So we can spin off a little while and we can nerd out on heat pumps as long as you guys want. So the first thing I'm going to talk about today is, why do we even want to implement a commercial heat pump water heating system? So gas systems are really common for all designers and plumbers. And so why do we want to go through the extra challenges of learning a commercial heat pump water heating system? And there are a lot of really good reasons. And the first is that simply throughout the West Coast and really throughout different parts of the country, codes and standards are transitioning to heat pump water heaters to address the climate crisis and try to mitigate some of those issues related to that. And the reason that we're shifting to heat pump water heaters as a potential alternate technology to gas water heating is because we want to minimize the carbon emissions on the grid. So here's an example that we see from California as a target to reduce the carbon emissions by 2050, reduce them by 80% below 1990 levels. So that's going to require a huge transition through all sectors. But what we're focusing on today is the building sector, which is a pretty decent chunk of the overall carbon emissions. So as soon as we transition that gas water heating load to a heat pump water heating, now we can both use electricity to handle that water heating, and also use a lot less electricity or a lot less energy to handle that load. So even if your grid is using gas to create that electricity, since we're operating so efficiently, you're still using a lot less gas overall. So one reason for the transition to heat pump water heaters is to reduce these overall carbon emissions. And there's a lot of cities throughout the country that are actually exceeding current plumbing codes. So there's these REACH targets, or these REACH codes in California, where a lot of cities are just requiring electric water heaters, or disallowing gas water heaters in new buildings. And in Seattle now we have a code in commercial buildings that requires heat pump water heaters as well. So this is really relevant throughout the country, but also extra relevant in Seattle and potentially throughout Washington State pretty soon here. And so on top of decarbonizing buildings, I talked about the potential for energy savings. So if you look at this graph on the left, we see that water heating is a little bit over 30% of the total energy usage in hospitals. So that's a really significant chunk, and that will change a little bit depending on the climate zone you're in, because your heating and cooling needs will change, but it's still that water heating load's a really significant chunk. So if we can cut that down by 1/3, or cut that down to 1/3 by using really efficient heat pump water heaters instead of electric resistance or gas, then we're going to reduce our overall energy consumption pretty significantly. So those are two big reasons that I brought forward today, but I want to hear an opinion from all of you. What is the most important reason for you to implement a commercial heat pump water heater system? Oops. Now I'll give you a little bit of time here as we wait for people to chime in. Yeah, reduce natural gas use and recover waste heat. So that's a really cool application for heat pumps as well, because as I'll talk about more later on, we're not creating heat with these heat pumps. We're just harvesting heat and concentrating it and putting it into hot water in this case. So if you have a waste heat load that normally you'd have to pay to get rid of by using extra equipment, now you can harvest that heat and use it for something effective. So decarbonization and saving energy are really great reasons to implement. And code requirements and not having a choice as well is still that's definitely a relevant reason to learn about commercial heat pump water heaters. We definitely want to be ahead of the curve as designers and implementers and contractors to make sure that we know what we're doing once inevitably we are required to install these. So we have a lot of training series through DNR and Ecotope to learn about heat pump water heaters, and this is just a 2-hour session, but there's a lot of others out there that we can get you a lot more information on this so you're ready once those codes do change and you need to install these systems. Yeah, energy efficiency and LEED certification is a big one as well, and environmental stewardship. Right? I want to use as little energy as possible and conserve my environment around me. And there's a lot of people with that same drive that even if you don't have to put a heat pump water heater in, you know that it's using less energy and decarbonizing and overall better for the environment. So I'm going to introduce how heat pump water heaters work before we talk about how they're implemented in the overall system. So when we think about heat pump water heaters, we can, as I kind of mentioned before, we're not talking about creating heat with electricity as we do with electric resistance, or creating heat with gas by burning a flame. We're actually just moving heat using the refrigeration cycle. So we're taking in this air that can be cold air all the way up to really hot air, but all of that air that is in the environment around us has a lot of heat in it, and we can harvest that from the air and then put it into domestic hot water in this case. And heat pumps have been used for a lot of different applications. We're talking about domestic hot water, but they're also used for space heating and cooling, like your air conditioner and your window or your overall central house system. And they're used in things like refrigerators by pulling the heat out of the fridge and exhausting that into the space around it. So heat pumps are very well proven out, and this is a really reliable cycle. And the application to domestic hot water is the only thing that's relatively new to these. So how a heat pump actually works is it's using the manipulation of pressures in a really clever way to be able to transfer this heat. Because if you think about transferring heat from 20-degree source air and pushing that into 140-degree hot water, that kind of goes against the second law of thermodynamics that says heat has to flow from hot to cold, right? But what we're doing here, I'll walk through how we can make that happen while still following this important law. So you can see if you draw a line halfway through this cycle, through this loop inside this heat pump water heater, half this circuit will be really high pressure refrigerant and half will be really low pressure refrigerant. And that happens because we have this compressor that's sucking refrigerant from this low pressure side and it's pumping it into the high pressure loop. And then on the opposite side of this loop, we have what we call an expansion valve that is slowly bleeding that refrigerant back off to the low pressure side. So now we have this compressor pushing refrigerant into this side of the loop and pressurizing that side, and then this expansion valve slowly letting the refrigerant return back to the low pressure side. So now we have refrigerant that's circulating around this loop, and half of this loop is high pressure and half is low pressure. So why do I keep talking about this high pressure and low pressure? That's because one of the characteristics of a gas is as soon as you increase the pressure, you're actually increasing the temperature of that gas. And as you decrease the pressure, you're decreasing the temperature because of the what's happening on the atomic level in that gas. So you might have seen this before when you're, say if you're spraying your keyboard with dust off, right? Is if you hold that gauge down, or you throw all that down and then most of that gas comes out, now your can is actually freezing cold. That's because the pressure inside that can has dropped significantly and quickly. So the gas that's remaining in that can has also dropped in temperature really significantly. So the same thing happens when you pressurize that can. It's actually going to get really warm. So what's happening here is we have this transition from low pressure to high pressure on this side of the loop through this compressor. So this cool refrigerant will actually, once it's pressurized, the compressor is not really heating it up, it's just pressurizing it. So that change in pressure is causing it to warm up significantly. So now we go from a cool refrigerant gas to a really hot refrigerant gas, and now that gas can exhaust that heat into 140-degree water. We'll say 140 to 150 typically. And then after it's exhausted most of its heat, now we're dropping back to low pressure, and the refrigerant can become extremely cold from that pressure transition. So now it's colder than the outside air. So now we're transferring heat from that cold air to an even colder refrigerant. So now our second law of thermodynamics is happy again because we're transferring heat from a warmer medium to a cooler medium. So we have low pressure, really cold refrigerant sucking heat out of the air and then moving to the other side of the loop, warming up significantly by changing to high pressure, and then exhausting that heat out into the domestic hot water. And really the only thing we're paying for here is the work done by this compressor to actually change that pressure. We're not adding heat, but we're doing work on the refrigerant. So we do have to pay for that in power, but since we're harvesting that heat from the air, now it only requires about a third of the power to put that heat into the water. So if you put 1 kilowatt of power in, you're getting about 3 kilowatts of heating out. And that changes with different variables like air temperature and the refrigerants you're using. But in general, that's a good rule of thumb. So now that we know how a heat pump works, it's important to think about how it operates as part of the overall water heating system. So we have our primary heat pump water heaters here, and they're paired with a primary hot water storage tank. And the main goal for this primary heating system on this side is for this system to take cold water in from the city and then heat it up to a reasonable supply temperature. So that's what you would expect out of any domestic hot water heating system, right? From your electric resistance heater in your closet to a large commercial system. We're just taking cold water and then we're heating it up to a temperature that works for that can come out of the tap. And then what we don't think about as much is this temperature maintenance system. And the job for this temperature maintenance system is to take the water that circulates through the building and maintain the temperature of that water to make sure that the water out in the building doesn't go cold before someone opens the tap and uses it, right? So we need to pretty much constantly circulate this water throughout the building and always replenish the loop with hot water. So then as soon as someone opens a tap, that hot water is ready to be used. So we have a dedicated temperature maintenance system in our heat pump water heating systems, because a lot of heat pumps are designed to take really cold water and raise it up to a high temperature. But the temperature maintenance system, you can see it's returning relatively warm water, maybe 110, 115 degrees, and then heating that water back up to a high temperature. So we either have to play tricks with the piping or use electric resistance, or use a heat pump that is designed for temperature maintenance heating that can handle those really high entering water temperatures. So we have the primary system that's heating cold water up to a high temperature using primary storage and primary heat pumps, and that's being sent to the building to be used. And then we have this temperature maintenance system that is heating really warm return water back up to a high temperature to be sent back out to the building. So then we always have that hot water on demand. And then the controls really tie all the components of the system together. And those controls can exist on the heat pump themselves, or they can be a third party or central controller, as we see in this schematic here. So now we'll talk about the importance between defining the importance of defining the difference between residential and commercial heat pump water heating systems. So we do have, it's important to define this difference because there are differences in codes and incentive programs depending on whether you're working with a residential or a commercial system. So the difference between these two systems, or the defining line, as explained by the Advanced Water Heating Specification, which serves as a standard for residential and commercial systems in different sections. A residential system serves less than 4 dwelling units. So if you have, say, a duplex with 2 dwelling units, then you'll have a residential water heating system. If you have less than those 4 dwelling units, or if you have a commercial load that is less than 6 kilowatts of input power. Right, and then, so that's where it gets a little bit confusing between residential and commercial, because a commercial heat pump water heating system can still serve a large multifamily residential load. Right, so between residential and commercial here, we're talking about the size of the system and not the occupancy of the building. That's a really important thing to remember. So we might have a residential heat pump water heating system in a commercial hospital or a commercial clinic because they don't have a large enough water load to require a commercial sized heat pump water heating system. So a commercial is more than 120 gallons of storage or more than 4 dwelling units of residential use. And residential is less than 120 gallons of storage and less than 6 kilowatts of input power, whether it is, say, a hobby shop or a single family home. And so we talked about residential and commercial systems in terms of overall system size, but there's also residential and commercial units as they're classified, or residential and commercial heat pumps as they're classified. So here I'll talk about a residential system that you might find in a small home, for example. And so this system always includes a heat pump water heater and a storage tank, right? Heat pumps do not operate well as instantaneous heaters, so we do want to pair them with storage so they have nice long run times that they need to be satisfied with. And then sometimes they might include a temperature maintenance system, a distribution loop, and a mixing valve, right? So that's if you don't have a really big hot water load, but you still have this big plumbing distribution system you need to send hot water out, then you might actually have that loop that circulates that water. So in my house personally, I don't have that distribution loop, and I don't have a mixing valve. I'm just heating up water and sending it out at the temperature that the heater is creating. But if I had a really widely distributed house, I would need that circulating loop. And then I might choose to add a mixing valve so then I can store that water at a higher temperature. And then a commercial system, on the other hand, is going to have, it's almost always going to have that temperature maintenance system. And a lot of times it's going to have these primary heat pump water heaters that are actually separate from the primary storage. So here we have, this is the basement of a multifamily building that we designed, where you can see there's 2 heat pump water heaters over here, and they're feeding this in-series storage here. So they're 2 separate components, and then we have the temperature maintenance system over here, and then we have a central controller that ties all these components together. And so if you're trying to find a system for a hospital or a clinic, you might ask, what should I actually install? Is it going to be residential or is it going to be commercial? And to determine this, you're going to first need to know what the size of the system needs to be. So first comes the system sizing, and then comes the determination whether it's residential or commercial, right? A small clinical setting or a small doctor's office might just need a residential system because they don't have the demand requirements that a commercial would. But if you're in a large hospital or medical center with a much higher domestic hot water demand, then you're likely going to have a commercial system that may be a little more custom engineered as opposed to the residential system that you might just find at a big box store as a fully packaged heat pump water heater that's integrated with the tank and everything. And then we get what could be a little confusing in this picture here. We have, say we have 10 or 15 residential heat pump water heaters, or residential type heat pump water heaters that you might find at Home Depot, but they're all plumbed together. So that makes this heat pump water heating system a commercial system because the total input of this system is much greater than 6 kilowatts. And the total storage is greater than 120 gallons. So even though we're using residential style heaters, they're plumbed together to create a commercial system. And so I talked about first you need to size your system, and this can be a little bit tricky with hospitals and clinics. When it comes to heat pump water heater sizing, we're going to size a little bit differently than you would a gas system, right? Usually we're not just going to count all the fixtures and use the Hunter's curve to determine what our peak load that needs to be satisfied by the heater will be. We're actually looking at the overall daily load and the profile of what that load looks like, right? So we have this really dialed in for residential and multifamily heat pump water heating systems because there's a really predictable load curve. Like there's the morning peak where everyone's taking their showers, and then there's the evening peak where everyone's washing dishes and then maybe taking showers after work and things like that. So we're using that load profile and the overall daily usage and occupancy in a multifamily building to determine how much storage we need to satisfy those peak loads, and then how much heat pump water heater recovery we need to recharge that storage throughout the day. Hospitals are a little different because there's kind of a variety of different occupancies in these hospitals and different mixtures of uses. So that profile is a little bit more difficult to predict. So what you're going to need to do when sizing a hospital system is you need to work really closely with the client to make sure that you understand what kind of loads that they're going to need. And so one source that has a lot of really good questions around this is the Domestic Water Heating Design Manual by ASPE. They talk about different user groups and different usages that you might expect in hospitals, and they talk about the questions that you should be asking these clients to basically build out that load profile throughout the day. So then you can implement the storage size to handle those really high peak loads when a lot of uses overlap, and then you can determine how much recovery you need to recharge that storage throughout the day. So I've thrown kind of a lot at you in a short period of time on a Thursday morning. So this is where I'd like to pause for questions. And so go ahead and throw those in the Q&A. And I'm sure Christy has a few good ones for me too.
Actually, our Q&A is pretty quiet, and I would love if someone could just throw like a, hey, hello, just to check to make sure it's working correctly. But I have a question for you, Evan. I feel like every time we're together and we're talking about commercial heat pump water heating systems, I learn something new. And watching and listening to what you were just saying, I realized like there's a lot of pieces and definitions and criteria. There's a lot of like stuff to think about, right?
Mm-hmm.
So what do you think, based on what you just told us, like what is your key takeaway about all this? If there was one thing to put a pin in and really hold on to it, what would that be?
Let's see. So that's a good one. I mean, one big key takeaway is you need to design these as heat pump water heating systems and not gas water heating systems, right? The sizing criteria is different, the piping's different. So don't make the same assumptions you would for a gas system, or else you might be like grossly oversized in your heat pump, for example, or it just might not be giving your heat pumps the conditions they need. So it's, yeah, education is key for these because we can't just make the gas assumptions that we all know.
Awesome, thank you. You saw you have another learner here too for like the watching intently. Eric, thanks for posting something in the Q&A to make sure it's working. Super appreciate it. Other than that, Evan, if anything else pops up, I'll let you know.
Okay, sounds great. Thanks, Christy. Yeah, so now we'll talk about the considerations we'll need to make to design around these heat pump water heaters. So that will include how these heat pumps are packaged, whether it's a unitary or a split system. It'll talk about the plumbing configuration we'll use with these, whether it's single pass or multi-pass, and then we'll talk about the importance of the refrigerant that's operating in your heat pump. So when we talk about unitary versus split system, a unitary heat pump for the sake of this conversation is a heat pump where everything is combined into one package unit. So you'll also hear this called integrated heat pump. So the storage, the controls, and the heat pump itself are all integrated into one package. So you'll see these a lot at for smaller residential applications, and these are the kind of heat pumps that you'll usually see at big box stores like Home Depot. And then the split system we're talking about today is when the storage and the heat pump are two separate items, right? And there's going to be plumbing running between the storage and the heat pump. So usually the heat pump will sit outside or in a buffer space, and then the storage will sit in the mechanical room. And I want to clarify that the split system we're talking about today is not talking about the refrigerant circuit. It's just talking about usually all the components in these heat pump water heaters, all the refrigerant components are in one package like we see in this Sanco 2 unit here. And then that is just plumbed separately from the storage tank. It's not that the heat exchanger is in a separate area than the condenser is not in a separate area from the evaporator. All the refrigerant's packaged in one spot, but it's sending hot water to a separate storage tank. So the configuration that's really important to think about when plumbing these are their single pass or multi-pass options. So a single pass heat pump water heater, it takes really cold water in and it heats that water up in a single pass before dumping it back into the top of the storage tank. So we can see over here that it's taking in cold 50-degree water from the bottom of the tank. It's just going to trickle that hot water through this heat pump so it has a long enough time to raise in temperature all the way up to 140 degrees before it returns it back to the storage tank. Alternatively, we have multi-pass heat pumps that operate a lot more like boilers, where they take in warm water from a mixed storage tank and then just with a really high full flow that's unmodulated, they dump as much heat as they can into that water. So you'll see about a 10-degree delta T through these heat pumps. So you'll have a much more mixed tank with those high flows and a smaller delta T with those multi-pass heat pumps. So the third thing that's really important to consider with heat pump water heaters is which refrigerant you're using in that heater. And refrigerants drive a few different things, a few different considerations that need to be made. One is the operating envelope of the heat pump itself. So depending on the refrigerant, your minimum operating temperature that you can effectively pull heat out of will change dramatically. So this is a performance map from a CO2 heat pump water heater. So what we're looking at here is we're looking at the intake air temperature on the x-axis, which is just usually the outside air temperature that this heat pump's operating in. And then we're comparing that to the capacity or the amount of heating that this heat pump can provide. So you can see as we increase in outside air temperature, our capacity or the amount of heat we can provide increases pretty significantly, which makes sense. It's easier to pull heat out of warmer air than it is out of cool air. But the important thing to think about in terms of refrigerant is you can see on this performance map, we're going down to about -10 to -15 degrees Fahrenheit air temperature. So these CO2 units can operate in really cold air temperatures, while an R134A powered unit, for example, can only operate down to about 40 degrees. So if you're in a really warm climate, then R134A heat pump would be just fine. Or if it's in a buffer space in Seattle, like a parking garage, then that would work really well. But if you're in much cooler climates, then CO2 might be a better option. And then the other thing to think about with refrigerants is the effective entering water temperature on the heat pump. So no matter what refrigerant you're using, a higher entering water temperature results in lower efficiencies because it's harder to push heat into that warmer entering water. But some refrigerants have much greater detriment when dealing with higher entering water temperatures. So you can see this performance map from a CO2 unit. If you have 120 degree entering water temperature, your capacity is way down here. So maybe 55,000 BTUs max. While if you have a 45 degree entering water temperature in that single pass arrangement, your max capacity is almost 200,000 BTUs. So that's almost 4 times what you would get out of the same CO2 unit if you're feeding it 120 degree water. Some other refrigerants aren't affected as drastically by that high entering water temperature. So you need to think about the refrigerant really carefully when you're determining how you're going to plumb your system and what kind of conditions you're going to put that heat pump through. And the other important factor in refrigerant considerations is the global warming potential, or GWP. And the global warming potential is a factor that determines how effective a refrigerant is at holding heat in the atmosphere as compared to CO2. So we all look at CO2 as the gas that is, well, it's one of the gases that is driving climate change because we're putting too much in the atmosphere and then it's holding on to that heat in the atmosphere and not letting it escape back out to space. So these refrigerants can do the same thing, but on a much greater scale, right? So say R410A refrigerant has a GWP of 2,088. So that means, and CO2, this is an important point, CO2 has a GWP of 1 because it's the baseline that we're comparing against. So if we release 1 pound of R410A refrigerant, that's equivalent to releasing over 2,000 pounds of CO2 in terms of how much heat that refrigerant is going to hold on to in the atmosphere. So this GWP here is a really big driver of future refrigerant technologies because, I mean, R410A is the most common, especially in hydronic heating, and that's 2,000 times worse than using CO2, while R134A is the other alternate that's 1,400 times worse than CO2. And it looks like we might have a question, Christy.
Yeah, go ahead and finish up here. The question is actually about the entering water and air temperature from before. So.
Okay. Yeah, I have a little bit more to say on this, and then we can definitely address that. So CO2 has its advantages with low temperature. It has its disadvantages sometimes with cost and complexity of that entering water temperature and driving complexity of plumbing design. But then there's one alternate that's been really well proven out in Europe, but has not taken hold in the US, and that's propane, or R290 as a refrigerant. It operates really well from a thermodynamic and refrigerant system design perspective, but the one thing that's holding it back is the flammability, right? Which we need to think about the relative safety here, because we're talking about a small contained charge of propane in a heat pump, and saying that's unsafe, but we also have unlimited amounts of natural gas flowing into almost every building today. So the reason I bring up propane is in hopes that someone in the audience in one of these conversations will know the right people to start driving the change to begin to allow propane into our industry as a viable refrigerant, because it works really well in terms of efficiency and really low GWP. It only has a GWP of 3 compared to the GWP of over 2,000 that a lot of heat pumps are using now. But yeah, it's got that, it has the standards. The standards are in the way right now to be able to implement that. Okay, so now we'll go back to Christy's question.
Yeah, so someone was just asking about the effect of the entering water temperature on heat pump efficiency, and for some clarification regarding if the water temperature is higher, it makes it harder for the heat pump to function. It lowers the efficiency, question mark.
Yeah, that's correct. So if we're heating water up from 45 degrees up to 140, now the water entering that heat pump, it's really easy to dump heat into 45-degree water. But then once that water temperature increases, now it's a little harder to dump heat into that. So, and then the CO2 refrigerant cycle that I'm not going to get into because it's really complicated, is a lot worse because of the phase change that has to go through and that the higher entering water temperature doesn't allow. So yeah, the simple answer that I over detailed there was higher entering water temperature equals lower COP or efficiency. Yeah, great question. And so now that we've talked about how heat pumps work and the considerations that you need to make around the heat pumps themselves, we can talk about some of the products on the market. So you can see this grouping on the left here. I have Unitary R134A residential heat pump water heaters. And some of these apply to small commercial as well. And these are what you'll find more likely in your garage in a single family home, or in closets or spaces distributed throughout buildings with small discrete loads, right? And then we have the split system single pass heat pumps. And I have CO2 separated out here just because with CO2 split system heat pumps, you're usually just going to put the heat pump itself located outdoors, and then you're going to plumb the hot water into a large storage tank. inside a mechanical room or something like that. So these CO2 heat pumps are usually, they're rated for outdoor installations, and they can handle those really low temperatures. So they can just have that, use that outside air directly. And then the R134A split system heat pumps, those can operate in single pass or multi-pass because they're less affected by those high entering water temperatures, but they don't operate that well in really cold air temperatures. So usually these will be used in really warm climates, or they'll be used in buffer spaces like parking garages, where you can use the heat from the ground and all the stored energy through the cement to warm that cold air temperature before it gets to the heat pump. So those usually aren't just installed directly outdoors unless you're in a really warm climate, like in Hawaii or down in Florida or somewhere like that. And when installing these heat pumps, it's important to talk about redundancy, especially in hospitals and clinical settings where a lack of hot water might actually be a life safety issue, right? So when we're installing these units, we want to have a target for what we call an N+1 redundancy. So what that is if you require 3 heat pumps, you're going to add 1 more heat pump, add a 4th heat pump to make sure if a single heat pump goes down, then you'll still have full hot water capacity. And so you can see an example here, like even if you have really reliable heat pumps, things happen, like a tree falls on your heat pump and now you have reduced capacity. If you have N+1 redundancy though, then you still have the full required heating capacity to meet your load, even though that heat pump's down, whether it's for maintenance or troubleshooting, or if a tree was to fall on it, it has to be replaced. When talking about this redundancy, though, we need to keep sanitation in mind, especially in hospitals where we have more delicate occupants. So if we do have redundant heat pump water heaters or a redundant electric heater, we want to make sure that that's not just sitting there turned off with stagnant water sitting in it, right? A lot of controls are capable of implementing these in cycles, in duty cycles. So it will actually switch off which heat pump turns on first. So it'll cycle through all the heat pumps in that configuration on a daily basis, because each time there's a demand for heat, it'll turn on a new heat pump. That makes sure that there's not stagnant water sitting in these units for a long period of time. So I want to have a quick check-in now. What are 2 or more words that summarize your key takeaways so far? And you can enter those in separately. And I'll just hang out here on this page for a little while. And here's what we can do actually. The next slide is a 5-minute break. So what we can do is we can turn that into 7 minutes. I'm throwing this on its head for Christy, but we'll turn that into a 7-minute break. And then if you promise to take 2 minutes to fill out the Slido, then we can go take 5 minutes and grab some coffee or whatever you want to do.
I think that's a great idea, Evan, and we're all good. Let's do that. Because we're at the hour mark, which I think is a great time anyways to like take a bio break, grab a second cup of coffee. When you get back, if you have a second to sit down, add to the Slido. Let's see what words we can accumulate into this word cloud. That would be amazing. Until then, I think okay. So we'll look at coming back at 11:07. How's that sound?
Sounds great to me.
Perfect. Okay. Well, I will see you in just a few then.
All right. See y'all soon. All right, I hope everyone's got their cup of coffee. Christy, did anyone chime in with any questions or anything else before
Nope,
we?
you're all good to go.
Great. Yeah, so while we were away, people came up with some really great words to highlight what we've talked about today. The biggest one is efficient, which makes a lot of sense. These heat pumps are a lot more efficient than any of the other competing technologies. And complexity is a fair word as well, right? There's a lot of things to think about with these units, but we want to make sure we keep in mind that the heat pump water heater manufacturers know all of the things that are required to make their heat pumps operate well. So in addition to that, we have a lot of really good resources through DNR Learn who's worked with Ecotope to put together all the information necessary to think about when we're installing these systems. So it can be pretty intimidating at first, but once you take the time and learn about some of these things, it all starts to make sense, and then you can get that backup from the manufacturers and the reps that deal with these heat pumps on a daily basis. So then, and they're more than willing to help usually, because them helping you design around what their heat pump needs means that they're going to sell heat pumps to you and your clients. So yeah, there's a wealth of information there as well. Then some other words here were reliable, redundancy, design solutions, refrigerant stewardship. These are all really great words that have a lot of power behind the drive to transforming the market to heat pump water heaters. So we had our 5-minute break, so we won't go to another. But now we can talk about the storage that's paired with these heat pump water heaters, which is actually really important because not only does it supply those really high peak demands when, say, everyone takes a shower at the same time, or all of this equipment's getting rinsed down with sanitized water, but it also allows the heat pumps to see the types of conditions that they like to see to operate most efficiently and reliably. So it provides that buffer to allow heat pumps to run for a long time, and the stratification in the storage tanks, depending on how we pipe it, will supply the proper supply temperatures that these heat pumps like to operate with. So the two things that we'll talk about today in terms of storage and its importance is the storage temperature and the stratification in these tanks. So storage temperature is really important for multiple reasons. One is because we want to prevent any bacterial growth, especially Legionella is a really big example. We want to make sure that the temperature of the water is at least high enough that this bacteria not only cannot reproduce, but is also killed by that water temperature. And the other benefit high temperature storage has is its effect on the effective storage capacity that you can supply to the building, right? If we have really high stored water temperature, that means we have to mix cold water in to deliver that at a good temperature to the occupants. So the higher your storage temperature, the more cold water you're going to mix in to deliver a certain number of gallons to the occupant. So a quick example here is if you have a 100-gallon tank of water that's set at 130 degrees, you're going to mix 60-degree water in with it, right, to create or to mix into 120-degree water for your occupants. That's going to get your occupants about 116 gallons of total water by mixing that 130 and 60-degree water together from that 100-gallon tank. But if that same tank at 100 gallons is storing 150-degree water and you're mixing 60-degree water in, now you can get 150 gallons of mixed water out of that same tank. So the same 100-gallon tank, instead of supplying 116 gallons of water nominally, it's now supplying 150 gallons because you're storing at a higher temperature. The other thing we need to think about, though, when we're talking about storage temperatures is the capability of the heat pump itself, right? If we say, well, we want a bunch of water potential out of this 100-gallon tank, let's just heat it to 200 degrees. That's that's fine in theory, but no heat pump's actually going to heat to 200 degrees. So you have to find that happy medium, because the higher the water temperature, the less efficient your heat pump's going to get in a lot of cases, because it's having to push heat into that much higher temperature medium. And you have to make sure that the water temperature you're storing at can actually be achieved throughout the entire year by a heat pump water heater. So there's some manufacturers that'll have brochures that say, yeah, we can heat this water up to 180 degrees, but they can only do it if the air temperatures maybe 60 or 70 degrees or higher. So then in the middle of winter, instead of storing that 180 degree water that you're set to, now you're probably storing 140 degree water. So if your system's designed around 180, you might have some negative consequences there. I talked about the importance of stratified storage in terms of serving the really low entering water temperatures to the heat pump water heater. So storage stratification is when the hot water is sitting on top of the tank, or sitting in the top of the tank, and then separately cold water is sitting on the bottom. Hot water is naturally more buoyant than cold water, so it will rise to the top of the tank. And if you're piped in a certain way and your flow rates aren't too high, then that tank's not going to mix up. You're just going to have these two essentially separate volumes of water within the same tank. But in a mixed tank, where you have really high flow rates and you're plumbed in a way that all of this is going to mix together, you have a much more consistent temperature throughout the entire tank. So these mixed tanks, we would expect to be paired with multi-pass heat pump water heaters, right? Because we have that. And as a reminder, the multi-pass heat pump is really high flow, but a really low temperature difference through the heat pump. So if your tank's at say 135 degrees, now you're sucking in close to 135 degrees into your heat pump, and then you're heating it up to 145. So the mixed tank's good for those multi-pass heat pumps, but if you have a single pass heat pump that trickles that really cold water through and heats it up to a high temperature, now you're going to want a stratified tank, because you have this cold water coming in the bottom of the tank and remaining cold, and then being heated by the heat pump, where it's then discharged to the top of the tank and it can remain hot. So the other big thing in terms of dealing with mixed or stratified storage is how these are controlled to turn the heat pump water heater on. If your entire tank is completely mixed up, then you're going to turn your heat pump water heater on based off the overall tank temperature of a temperature sensor in this tank, right? As soon as you start drawing water out, the entire tank temperature is going to lower. So your heat pump might turn on when your entire tank is at 130 degrees based off a temperature sensor located somewhere in the middle. But with a stratified storage tank, we don't have that overall consistent tank temperature. So if my temperature sensor is right here in this tank, even though a third of my tank is filled with 50 degree cold water, my temperature sensor still might be reading 140 degrees. So my temperature sensor here is not indicative of how full the tank is just based off the temperature alone. What we're going to see is as hot water is drawn out to the building and cold water is brought in the bottom, now cold water will start to fill this tank from the bottom up, and this little yellow layer here will be sucked up to the top of the tank as the hot water is drawn out the top. So this sensor located right here will go from 140 degrees down to 50 degrees in a really short period of time. So we're going to tell the heat pump to turn on based off this temperature sensor dropping significantly in temperature. And so that means the location of this sensor is really important, because if we don't turn it on until the sensor's cold up here, now your entire tank's empty before your heat pump turns on. And so the other thing we can think about with storage, I thought there might be a question after that one. What do you have for me, Christy?
Actually, this is, well, speaking of storage and temperature, what are the safety measures that can be used to prevent scalding from that super hot stratified water?
Oh yeah, great question. So when dealing with the really high tank temperatures and high storage temperature that's usually required in commercial buildings, we're definitely going to want to install a reliable mixing valve, right? In domestic hot water systems, it has to be a domestic hot water mixing valve, right? So that's how we're able to mix the hot and cold water together and supply those occupants with water that's not going to burn them. Yeah, great question. So when plumbing these tanks in, there's two very different configurations that you can plumb them in, and they both have their advantages and disadvantages. And the two configurations that we'll talk about today are parallel plumbed tanks and tanks plumbed in series. So we'll talk about the flow constraints. We'll talk about the effect of maintenance and redundancy with these two configurations, and we'll talk about the challenges of balancing. So in terms of flow and these two different configurations, you can see no matter what configuration it's in, the building flow will be the same, right? And the building flow you can imagine being here, like the total required flow going out to the building at any point in time will be equal here for hot water coming out, and then cold water coming in to replace it. So if you have two tanks plumbed in parallel, you can see that if you have, say, 10 GPM going out to the building, that's only going to require 5 GPM out of each tank because they're both supplying that load equally, right? And same with the cold water coming in. If 10 GPM is coming in to make it up, now there's only 5 GPM going through either of these inlets to each tank. So you can have much higher maximum flow rates to the building by plumbing in parallel because they equally share that load. Plumbing in series, on the other hand, you can see there's just one single path for that entire flow to go. So if you have 10 GPM going to the building, you also have 10 GPM going through each tank and each inlet and outlet. So your maximum flow capabilities are a lot lower unless you specify tanks with much larger connections. And if we talk about redundancy, which is really important in hospitals, we talked about redundancy for the heat pump water heater itself, but we also want to make sure that we have redundant storage in case a tank needs to come down for maintenance or replacement. So in a parallel system, if we require one storage tank, but we put in a redundant storage tank, now if a tank needs to go down for maintenance, all you have to do is put in these extra valves on the inlet and outlet. And now just closing these two ball valves, this entire tank is isolated from the system. So you can do whatever you want to it, while this tank is still handling the load just fine. In a series configuration, on the other hand, since the entire flow goes through every tank, just isolating the inlet and outlet of a tank will actually cut the flow off from the rest of the system. So you're basically causing a close in this one single line going to the building. So you have to get creative and you have to put in these bypass lines, right? So then if you close one tank down, you can open up a bypass line to basically flow around that tank, so it's not cutting off the flow. But the downside to that, especially in hospitals, is now when these bypass lines are closed, you have stagnant water in these lines. So that's kind of a big no-no in hospital design and makes plumbing redundant tanks in series a little bit more challenging. And so right now, parallel tanks look a lot more promising than tanks plumbed in series, and they're a lot more common in gas systems too. But the reason that we plumb these tanks in series so often in a lot of applications is because it makes for a lot better balancing of flows, right? If you're dealing with a parallel tank setup, you could have, say, 2 to 5 storage tanks here, and if the pressure drop through any of these tanks is inconsistent with the rest, then the flow entering and leaving that tank will be inconsistent with the flow through the rest of the tanks. And we've talked about the importance of stratification and using that stratification layer to gauge when to turn that heat pump on. So if your flow is uneven between these two tanks, that will really affect your control, because now if this tank on the right here is draining down more quickly than the tank on the left, this stratification layer isn't going to be in the same spot in either tank. So now if you're controlling off the temperature in this tank, and this is drawn down really far, but this tank is still full because it's not flowing very much water, now you're turning your heat pump on potentially too early for this tank. And now as it recharges, if this tank completely fills up before this tank does, and this tank is in charge of turning that heat pump off, now that heat pump's seeing really high entering water temperature because the hot water from this tank is mixing in. So it's also important to balance your heat pumps as well, because you want to recharge your tanks at an equal rate, and that's equally as important as discharging your tanks at an equal rate. So that's not really an issue with in-series tanks, because you just have that one single flow. So any pressure drops throughout this system will result in a change in flow throughout the entire system, rather than a change of flow through an independent tank. And same with the heat pump balancing itself. All the heat pump flow is just going back into this final tank and back charging through the entire series. So you can't disproportionately charge tanks in a series configuration. So this is where the in-series model really shines, is because you don't have that imbalancing of stratified storage tanks that could lead to controls issues and overall lower effective storage capacity. So if you do go with a parallel setup, because say in an office or a hospital application, you need that redundant storage, then you just need to make sure that the pipes are completely identical from each tank to the supply to the building. See here, you have an equal length and equal number of bends from both tanks before they merge and contribute to this supply line. Same with the heat pumps, right? You have the same number of bends going back to the heat pump supply in return. So now we have equal pressure drops, and we'll be able to maintain that balance between the tanks. One more thing we'll need to think about with storage, especially in a hospital setting, is sanitation. So we need to make sure that we develop a maintenance schedule for the building maintenance to flush these tanks regularly and make sure that there isn't any sediment build up in the bottom of the tank that will harbor bacterial growth. And this flush is really easy, because if you say you plumb this drain to a floor drain in the mechanical room, then once you open this drain pipe, you don't have to drain the tanks completely. You can actually keep the water supply to the tanks open, and it will just basically shoot water out this drain and keep replenishing it through the plumbing setup that's already, through the cold water makeup setup that's already there. So all you have to do is just open this drain up, and it'll flush all the sediment out on a regular basis, and then that's really good to maintain sanitary tanks. And then there, I'll pause for questions and see if you guys have anything. And yeah, is there any questions out there yet, Christy? Great.
Yeah, one just popped up. How do you keep the series option, that middle tank in it? How do you keep that warm? Because the schematic showed that the hot water was provided by the heat pump to only the hottest tank. So yeah, so we're looking at the series option, that middle tank right there that has the actual like migrating band. How do you keep that one warm?
That's a great question. Yeah, so I'll get rid of the heat pumps for now. And so imagine all of these tanks are charged right now. We'll talk about flows to the building. All of these tanks are charged. Now you have hot, 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 and you can see the top of the first tank is plumbed to the bottom of the second tank, and so on and so forth from the second to the third. So you can imagine these as one really tall storage tank, right? The top of this tank is connected to the bottom of this tank. So as we discharge these tanks, the cold water comes into the bottom of this tank series, we'll call it, and then it just keeps on working its way as this hot water is drawn out from the top of the tank. But when we're recharging it with the heat pumps, the opposite happens. Right now, the flow of water is actually going into the top of the tank, and it's being pulled from the bottom of the tank in series. So now we're filling this top tank with hot water, and we're actually back charging it. And then once this tank is completely full of hot water, that will then work its way to the middle tank, and it will completely charge that middle tank with hot water as the cold water is being pulled out of this line and into the heat pumps. So then as that tank is full, now that hot water is going to work its way back to this first tank, and the heat pump will shut off once it sees hot water entering the heat pump. So now we've actually we've backfilled all 3 of these tanks with hot water. And I keep pointing to my screen as I'm talking about this, but hopefully it follows without you actually being able to see my finger.
We can see your mouse moving, so that's perfect. That's the only question we have right now.
Okay, great. So now we'll move on to the considerations we need to take when we're designing the temperature maintenance system, which is the system that's heating that recirculated water. So the main goal, as a reminder, for this temperature maintenance system, excuse me, is to keep the water in the distribution loop hot. Right? If you imagine these are all different taps, just as they're shown, say different showers, and then we have plumbing that has to run out to each tap. If none of these are in use and we have previously sent hot water out to these, it'll start out hot, but then that water is going to cool down, right? And then once these taps open, now we're going to have to flush all of that cool water out of the pipes before the hot water can make it there. If it's a big distribution system, then that could take a really long time with say a 1 GPM flow rate. So what we do is we're going to supply a return line, and then we're going to circulate hot water throughout these lines so it doesn't get a chance to cool down before it's used. And then it's really important, though, to balance how much water is going through each one of these lines, because if we don't have any sort of balancing, then the water is going to take the path of least resistance. So we'll have a lot more circulated flow through this really short loop compared to the flow through this long loop. So we want to basically provide extra resistance in those loops that don't have it naturally, right? And we'll do that with balancing valves, right? And there's a couple different strategies for balancing valves. The most common I've seen are these manual circuit setter valves. And the downside to those is a plumber has to manually adjust every branch loop with these valves. And sometimes you might have 20 branches, right? And then once you adjust, say you adjust the first 3 branches and get the flow perfect, as soon as you start shutting down the farther loops and increasing the pressure drop there, now the flow actually changes in these first loops. So you have to reiterate and readjust all those valves again until everything's within spec. So that's not super realistic from what we see in the field. So an alternative here that doesn't require this manual balancing is a thermostatic balancing valve. They will adjust automatically based off the temperature in these branches, which helps a lot because now you don't have to adjust these based off the actual flow through the loop, which will vary as these taps turn on and off. It will automatically adjust the flow to maintain a perfect temperature to these fixtures at all times. And it will also prevent overheated water from returning to this temperature maintenance loop, which is a lot more difficult for a heat pump to heat if we're using a temperature maintenance loop that is employing a heat pump to reheat that water. So we have a few different strategies to handle this temperature maintenance load. And the first is a return to primary strategy, where we have it returns back to the primary system for heating, and then we have a parallel temperature maintenance tank that we'll talk about, and a an in-series or swing temperature maintenance tank. So with the return to primary tank, you can see here it looks a lot simpler than the other temperature maintenance configurations, because you don't have to have a dedicated temperature maintenance system. You're returning that hot water right back to the primary system, just like you would in a gas water heating system. Right. The downside to that is now if you don't have a lot of cold water coming in and mixing in the bottom of this tank, now you have much higher entering water temperatures to the heat pump water heater. So this is only compatible with some manufacturers. Looks like the neighbor's home. Sorry. This is only compatible with some manufacturers because I talked about some manufacturers, especially those from CO2, really don't like that high entering water temperature. So you have to make sure your manufacturer is on board with this strategy if you're going to implement that. And this will usually have a lower first cost tied to it because you don't have that dedicated storage tank and dedicated heat pump to handle those temperature maintenance losses. You do have, on the other hand, though, have to increase the size of your primary heat pump water heater because you have a larger load to satisfy with that primary heater. But in hospitals, if we're talking about requiring a redundant heater for every system, then now we just require that redundancy for the primary heater rather than requiring a redundant temperature maintenance storage tank and redundant temperature maintenance heater. And since we talked about in the stratified storage tanks, we talked about the temperature sensor actually registering a really high drop in temperature before the heat pump turns on. You have to be careful with this return to primary system because you might not see that drastic temperature drop if most of your load is hot water return. In a stratified storage tank with a separate temperature maintenance load, you might turn the heat pump on when this temperature sensor reads 100 degrees because that's when the cold waters hit the temperature sensor. But if your hot water return load or that temperature is 115, now your tank's filling with 115 degree water if you don't have a lot of hot water usage and cold water coming in. So now your heat pump's not actually going to turn on. So you have to be really careful with those control set points and have the manufacturer rep help you pick those out. And then the hot water return temperature is also very important because even though these heat pumps are designed to handle higher entering water temperatures, they're still a lot more efficient and reliable if we are able to minimize this return temperature. So minimizing the loop temperature and what that returns at through proper balancing will allow this heat pump to work a lot more reliably and efficiently. So an example of a return to primary system you can see here is actually has these parallel plumbed tanks. And then what's actually out of the picture is we have the cold water and the hot water return both plumbed into the same line, returning to the bottom of this primary tank, as well as the inlet to the heat pump water heater, right? Which we don't do that at Ecotope because we like to have that hydraulic separation between the heat pump and the storage tanks. And whenever you have usage, that throws off the pressure going to your heat pump. But I'm diving into the details a little more than intended. But yeah, the main focus of the return to primary system is that hot water return line is actually going directly back to these primary tanks. And then the second temperature maintenance strategy that we see common here is the parallel temperature maintenance tank. So what we're doing here is we have our primary storage and primary heat pumps serving the domestic hot water load as it's being used by the occupants. And then we have a completely separate temperature maintenance system heating the full temperature maintenance load or this recirculation load here. And these are basically supplying the mixing valve separately with hot water to be able to satisfy these two flows. And so this system works really well when the temperature maintenance load is really high compared to the domestic hot water usage, because we still have a a piece of equipment that's been optimized to handle this temperature maintenance load separately. So we're heating it at a relatively high efficiency versus the lower efficiency that this heat pump would experience if it was to see those higher entering water temperatures. So we can optimize this primary heat pump to heat really cold water, which is the much larger percentage of the load, and then optimize this smaller heat pump to heat really warm water. And so the challenge here is there's only a few manufacturers that can supply a heat pump that can handle those high entering water temperatures. And yeah, as I mentioned here, the efficiency of this primary system is really, really high. And then the efficiency of the temperature maintenance system is still pretty high, like still much higher than electric resistance. And then a reminder that the return temperature back to this tank is still really important because there's still limitations even for heat pumps optimized for this kind of load. So an example of this is from a building in Seattle where we have a couple of Colmac heat pumps serving this load, and we have the heat pump on the left here is the primary heat pump that's charging these primary storage tanks in series here. So we have five primary storage tanks charged by this one heat pump, and then we have this temperature maintenance storage tank that's charged by this separate heat pump. You can see these heat pumps look identical, but they are running in different modes. Like this is a multi-pass heat pump that's optimized for that temperature maintenance load, and this is a single pass heat pump optimized for the main load, the primary load. And then the last temperature maintenance strategy that is a little bit more interesting is the in-series or swing tank configuration. So what's going on here is we still have two dedicated systems, but they're not completely separate from each other, right? If we follow the lines from the cold water supply from the city out to the supply to the building, we can see the cold water comes in, it's heated up to a high temperature from our primary heating system, the heat pump and the storage paired together, but then that hot water actually flows directly through the temperature maintenance heater. So now, since this is this has to be a higher temperature than the temperature maintenance tank, but now the supply from the primary heating is actually transferring heat into this temperature maintenance tank as it flows through and goes out to the building. So if there's enough demand from the building to drive this primary flow to be really high, now there's enough primary flow to actually heat this temperature maintenance tank without any additional heating required. But if there's no usage from the building, now we don't have that flow from the primary system to supply and feed through this temperature maintenance tank. So that's when this loop that is consistently trying to cool this tank down will essentially cool that tank down to the point where we need some sort of auxiliary heating. So whenever there's high usage and low temperature maintenance losses, this system will operate at the efficiency of this primary heat pump this primary heating system, because it's passively heating this temperature maintenance tank as it flows through it. So we want to make sure that we implement this system when the temperature maintenance losses are really low compared to the usage. And any single pass heat pump can be used to be paired with this primary storage. So it offers this basically offers a solution for every manufacturer that has a single pass heat pump. And usually just to keep costs down and improve reliability of this temperature maintenance tank, this will be an electric heating element, because a lot of the heating load for this temperature maintenance loop is offset to the primary storage. So we have a low load that's required by this heating element. And this is actually a really good solution for retrofits, because if you look at this temperature maintenance system on its own, you can see this actually looks a lot like a conventional water heating system, right? You have the water inlet that's normally coming from the city and bringing cold water into the system. it's supplying a mixing valve that sends tempered water out, and it's accommodating that hot water return and reheating it. The difference here is instead of sending cold water to this temperature maintenance tank or this conventional water heating system, we're going to heat all of that water that's coming in with an efficient heat pump and then send it to the conventional water heating system. So we're essentially plumbing a heat pump water heater system upstream of the existing system, and we're able to use whatever heater already existed there to handle those temperature maintenance loads that aren't being handled by the primary system when there's a lot of usage. An example of this swing tank system that that worked really well is I believe this is Elizabeth James' house in Seattle. And what we're doing here is we actually were able to reuse all of the storage tanks as well as the electric water heater that was the primary heater for the system before we installed the heat pumps. So you can see these instantaneous electric heaters on the wall back here. These are now plumbed directly to this temperature maintenance tank or the swing tank. And then we plumbed the heat pump water heaters to these primary storage tanks. So these are now plumbed basically upstream of the existing water heater. So then we're heating all the water's coming in from the city, we're heating it up to 150 degrees with these Sanco 2 heat pumps. And then we're sending that through the temperature maintenance tank, which will passively heat that temperature maintenance tank as that overheated water is being sent to the building. And then we install the thermostatic mixing valve here just in case this temperature maintenance tank overheats with a lot of usage. So now no matter what this tank temperature is, between 130 and 150 degrees, we're still supplying 125 to the building consistently. So now I'll put these temperature maintenance strategies side by side and just a quick high-level overview. So we have the return to primary, where the hot water return goes back to the primary heating. And then we have the parallel temperature maintenance tank, where the temperature maintenance or the circ loop is handled completely separately from the primary load. And then the swing tank, where the primary load is handled by this primary heating system, but it's sent through the temperature maintenance system, which passively heats this temperature maintenance tank during terms of high usage. And with that, I'll pause for questions and probably hang out on this slide because there might be some questions about temperature maintenance strategies. Oh, I think you're muted, Christy.
Yeah, thanks. There is a question about what type of system would be best suited for a hospital with 24/7 operation. And I've just let folks know in the chat that that's actually the next section, I believe, is all about hospitals and clinical settings and your suggestions moving forward, right?
Yeah, that's a great segue.
Cool.
And let's see. I don't know if there might be a couple slides between now and then, but we'll see. It'll be a surprise for both of us.
It's coming.
I just see the slides and let them speak to me. No. Yeah, so now we'll talk about commercial heat pump water heaters for hospital and clinical settings specifically. Up till now, we've kind of just talked about the heat pumps themselves and not totally how they apply to actual hospitals, but this is where we'll dive in a little more deeply there. So we need to know what kind of system we want to install into the building we're using, right? So we'll kind of rate these three different options for temperature maintenance configurations accordingly. So option one was the parallel temperature maintenance tank, and we're giving that 5 stars for efficiency because slow network connection. Christy can jump in and let me know if I'm laggy or anything. But we're giving this 5 stars for efficiency because we are using a heat pump water heater to heat the full temperature maintenance load. So this type of system is really good when there's really high temperature maintenance losses. So maybe if you have a really big building that doesn't have a ton of domestic hot water usage, but you still have to circulate hot water throughout the entire building. That means you're going to have a really high temperature maintenance load that should be satisfied by a dedicated heat pump water heater. So this is going to cost a little bit more because you have you have to buy heat pumps to handle this load, but it pays off in efficiency in that application. So the return to primary system, we're going to call this a little bit less efficient because it's employing this really large primary heat pump water heater to heat this warmer temperature maintenance load. But this is going to be lower cost because you don't have that dedicated temperature maintenance system, and you're going to want to install this when you require multiple heat pump water heaters, because there's going to be times, especially at night, when there's really low domestic hot water usage, but you still have that circulation load. So you have a relatively low load compared to what this primary heat pump can handle. So if you have, say, 3 heat pumps in this system, you have your N+1 redundancy and then 2 primary heat pumps, then now you can just turn 1 heat pump on when you have primarily temperature maintenance load, and then you can turn more heat pumps on as your domestic hot water usage ramps up. And then the third option was the swing tank option, right? And this is, well, we give this, it's kind of hard. It's a little hard to rate this one generally in terms of efficiency, because if you actually do have a building with relatively low temperature maintenance load, maybe all the fixtures are pretty close together, but you have a really high usage, now you have extremely high COP for both loads because you have this primary heating system supplying the entire heating load, right? So if you, on the other hand, if you have a really high temperature maintenance load and not very much usage, now you have almost full electric heating, heating that temperature maintenance load. So that's why efficiency really varies here. And if you have a really high usage and low temperature maintenance application, that's what you want for this. This is also really good for retrofit systems for the reason I explained earlier, where we already have this existing water heating system that can serve as the temperature maintenance system. Yeah, so those are the considerations for heat pump water heaters and the different systems that we talked about. And so the final thoughts here are, there are definitely some pros and cons in installing these systems in hospitals and clinics. So some big pros here are the decarbonization and energy efficiency that we talked about, and being able to satisfy the codes and regulations that are increasingly prevalent in a lot more jurisdictions lately. And then we're talking about hospitals where there are a lot of people with respiratory issues. So one thing we didn't touch on yet is the local air quality that these heat pumps will help out with, right? A lot of boiler systems that are employed to both heat buildings and heat the domestic hot water load, they're exhausting that boiler exhaust gas right into the air surrounding these buildings. So if you have a lot of patients with respiratory issues or just the general population, that's putting all these gas emissions into your local air volume is going to be really detrimental to your health there. So heat pump water heaters, all they do is cool the air around, so they don't have any of these local emissions. And then another pro of heat pump water heaters is the safety that comes with having a contained charge of refrigerant rather than a an unlimited amount of gas flowing into your building that could leak and potentially explode. Some cons for these heat pump water heater systems, one is going to be the price, which you have to think about when you're thinking about budget costs for the entire project, but there are a lot of incentive programs out there to help mitigate the price differences. And then the other big con here that I'm sure some of you are experiencing right now is the comfort level of designing and implementing these systems, right? There's a lot of lessons that you have to learn, and there's a lot more communication that's going to be required between the manufacturer, their rep, and the designer and the installer, because there's not a, this is exactly how you install heat pump water heating systems, and this is what every manufacturer agrees with. There's, well, this manufacturer has these considerations to think about. So that communication is really, really crucial, and that will help comfort the designers a little more and address this challenge. And we do have some studies that we should be able to send out to you guys from other countries that are using heat pump water heaters really successfully in hospital settings. There's some case studies from, I think, different countries in Europe. Christy found these a while back, so I won't put her on the spot to explain exactly what they are unless she's totally on board with it.
I think anything that you can go and explore yourself to learn more about is really valuable. And the next step in this is actually to hand back control to Sean. And I know, Sean, your intent was to also share the slide deck and to make sure this video is available. And so those things, along with all the links and the resources in here, will become available to you folks, the learners, in case you want to go and explore more on your own.
All right. Yeah, so as Sean has, oh, we do have a recap slide, which I think I covered pretty well in the final thoughts. But as Sean goes over all the cool happenings at Seattle City Light, we can open this exit survey for you guys to go through.
If you could, if everyone here could grab like their smart device, their tablet, a web browser, and just open it up, you'll see that this exit survey has 5 questions. 2 of which, the first 2 are ones that we could post here, like what questions remain for you and what are your key takeaways. The other 3 questions are a check-in for did we meet your needs, and they won't show up. Those are private. Those are things that we collect as we debrief afterwards and say like, hey, is this hitting all the goals here? Are we meeting our learners' needs? Are we attending to why they are attending? So if you could take a moment, fill that out. We'd be super appreciative. Evan, I think you have to keep that slide open for the survey to be open, but as long as you're on your screen with it open, then it should be available to everybody else.
Great. Yeah, I'll test it as well too. Make sure I'm on the right slide.
Evan and Christy, thank you very much for all of that. Great presentation. While the Slido is still available for you guys, I will go back to it in just a moment. I'll give you presenter back, Evan, so you can hit those if you'd like. But in the meantime, while you are all going ahead and filling that stuff out, just a couple of final words. Thank you. This has been a presentation from the Lighting Design Lab, Seattle City Light. We have some additional educational opportunities coming up. Next week, or the next 2 weeks, we'll have Energy Management Systems, Part 1 and 2, same time, same place. Following that, in 1 week, note, one is on a Tuesday and one is on a Thursday, we have Commercial Refrigeration, Part 1 and 2. And then the week following that, we have Adjustable Speed Variable Frequency Drives, Part 1 and 2. So several mechanical system classes coming up, although the energy management system will bridge mechanical systems, lighting, all of that kind of good stuff. And then finally, as we round out our webinar series for the spring summer, Armando Berdil and I will be providing you with a recap of everything that we've seen at Light Fair on July 14th. Of course, if you have any questions on any of this stuff, please go ahead and contact me or Lighting Design Lab at seattle.gov. And the reminder that, as Christy has mentioned, slides and the actual recording will be posted on our webpage within a few days. We are City Light. Please go ahead and take our survey when you leave as well. That will be very helpful. And now, Evan, I'm going to hand it back to you as presenter, so that if you would like, do you want to show people the results of the Slido? I suppose I should ask you that.
It's up and running, so I think we just leave it there. We would love to have as many folks fill it out. You know, we're always trying to grow our skill set. I'm so glad, Sean, that you're sharing upcoming trainings. I was part of the development team for all of those, and the energy management systems, not to like pick favorites, but that is one of my most favorite courses because it's so interesting. I learned so much building it, and Michelle Sagehorn, the SME who presents, is incredibly knowledgeable, so down to earth, and she's just kind of like fun to chat with. So if I could like push some, like you should attend this, it's a great course. It's a great webinar series.
So you heard it here first, folks. Go ahead and tell all your friends. Come on, come all. We have plenty of room in the space. Then, if there's not a reason to go back to the Slido, then why don't we say once more, everyone on the call, thank you for joining us. Always a pleasure to be able to provide additional educational opportunities for the community throughout the Northwest here. Evan, thank you for another terrific presentation. Christy, thank you for helping to develop all this stuff and being a great moderator. And with that, then I will say, if you're in Seattle, hopefully you're in an area like me where the sun just popped out. So you guys all have yourselves a terrific sunny afternoon. Take care, everyone.
Thanks, everyone.